While the world was busy watching Cybertruck deliveries and arguing about full self-driving, Tesla's engineers were quietly solving a problem that's plagued the entire electric vehicle industry for over a decade. It's a problem that shapes the cost, the geopolitical balance, and the true environmental cost of almost every EV on the road today. What if Tesla could build a motor just as powerful and efficient as their best designs, but without the one part that's the most expensive, the most controversial, and almost entirely controlled by a single country? What if they could get rid of the EV revolution's biggest weakness? Well, it looks like they've done it, and almost nobody saw it coming. At their 2023 Investor Day, Tesla's then VP of Powertrain Engineering, Colin Campbell, dropped a bombshell the industry is still wrestling with. He announced that Tesla has designed its next-generation drive unit to use 0 rare earth elements. But what he didn't spell out, and what's become clearer in the months since, is that Tesla wasn't just planning to swap one type of magnet for another. Their real goal seems to be way more radical. They appear to be engineering a future with no magnets at all. Today, we're breaking down what that really means. This isn't just a new motor, it's a total shift in thinking. We'll get into the dirty secret of rare earth magnets the industry avoids talking about, trace Tesla's decade-long quest to break free from them, and show how new technology is making the impossible possible. This is the story of how Tesla's new magnet-free motor changes everything. To get why this is such a huge deal, you first have to understand the part that makes modern electric cars go: the permanent magnet motor. For years, the gold standard for EV motors has been the permanent magnet synchronous motor, or PMSM. These things are incredibly efficient and power-dense, so you get a lot of power from a small, light package. This is the magic behind a Tesla's instant acceleration and amazing range. The magic ingredient? Strong, compact, permanent magnets. And for the last 30 years, the best permanent magnets have been made with a group of elements called rare earths, specifically neodymium and dysprosium. They aren't as rare as the name suggests, but mining and processing them is incredibly difficult and destructive. The process uses a nasty cocktail of toxic chemicals to separate the elements from the ore, often leaving behind radioactive wastewater and poisoned soil. The environmental cost is huge, but the geopolitical cost is just as scary. Today, over 90% of the world's rare earth processing is controlled by one country, China. This gives them a strategic stranglehold on a key component for the future of transportation and clean energy. Any trade spat or political tension can make prices for these materials explode, wrecking the production plans and budgets of car makers like Ford, GM, and even Tesla. Think about it. The Western world has gone all in on an electric future, building a multi-trillion-dollar industry on a foundation that's almost completely controlled by its main economic and geopolitical rival. That's a supply chain risk that keeps CEOs and national security advisors up at night. This is the dirty secret of the EV revolution. The push for clean energy is tied to one of the dirtiest mining processes on the planet and a very fragile geopolitical situation. Every car maker knows this can't last. They've all been looking for a way out. Some have tried using fewer rare earths, especially the priciest ones like dysprosium. Between 2017 and 2022, Tesla themselves made huge progress in cutting down the rare earth content in their motors. Others looked at different magnet materials. For a while, the popular theory was that Tesla's next motor would use ferrite magnets instead of rare earths. Ferrite magnets are made from iron and oxygen, basically rust. They're super cheap and abundant. The supply is nearly infinite. The catch, they're much weaker than rare earth magnets. A motor using ferrite magnets would have to be a lot bigger and heavier to make the same power, which is a big hit to weight and efficiency. For example, simulations by the company Proterial suggested a ferrite motor could be up to 30% heavier to match the performance of a rare earth motor. For a company like Tesla, which is obsessed with efficiency, this seemed like a compromise they would never make. So the industry was stuck. Do you pay the steep price, financially and environmentally, for powerful rare earth motors, or do you accept the performance hit from cheaper, more common ferrite magnets? It looked like a puzzle with no solution. But what if the question was all wrong? What if the answer wasn't to find a better magnet, but to get rid of magnets completely? This is the genius of Tesla's new plan. They're not just changing the recipe, they're throwing out the cookbook and starting from scratch. To really get the importance of a magnet-free motor, you have to look at Tesla's history. This isn't some sudden change of plans. It's the result of a long, deliberate journey. In fact, it's a return to where they started. When the original Tesla Roadster and Model S came out, they didn't use permanent magnet motors. They used AC induction motors. This was a specific choice by co-founder and then CTO J.B. Straubel. An induction motor is a thing of beauty in its simplicity. It has two main parts, a stationary stator on the outside and a spinning rotor on the inside. You pass an electric current through the stator's copper windings to create a rotating magnetic field. This field induces a current in the rotor, which then creates its own magnetic field. The dance between these two magnetic fields is what makes the rotor spin and turn the wheels. The great thing about an induction motor is it has no permanent magnets. The magnetic fields are made purely by electricity. That means no rare earths, no geopolitical drama, and a lower cost. So why did Tesla ever switch? The main reason is efficiency. Permanent magnet motors are just more efficient, especially at lower speeds in city driving. Because the magnets in the rotor are always on, you don't waste energy creating that magnetic field, it's just there. This directly translates to more range from the same battery, which is the most important number in the EV world. So when designing the Model 3, Tesla made a strategic change. They wanted the Model 3 to be a car for the masses, which meant getting the most range and performance possible while keeping costs down. So they developed a wild new motor, an interior permanent magnet synchronous reluctance motor, or IPM-SRM. This was a hybrid design. It used strong rare earth magnets inside the rotor, but it also cleverly used the shape of the rotor to create extra reluctance torque. It was the best of both worlds, the high efficiency of a permanent magnet motor with an extra kick from the reluctance effect, all in a small package. It was a masterpiece of engineering and a big reason the Model 3 became the world's best-selling EV. But the rare earth problem never disappeared. Even while Tesla was enjoying the success of their new motor, their engineers were already figuring out how to escape the trap. They started re-engineering the motor to use less of the most expensive rare earths, like dysprosium, which helps magnets handle high heat. With smart design and better cooling, they found ways to use less of it, or none at all, without hurting performance. It was a small but crucial step. Then came the 2023 Investor Day, where Colin Campbell announced their next goal, a permanent magnet motor with 0 rare earths. The industry instantly assumed they'd cracked the code on ferrite magnets, somehow beating the weight and size penalties. The engineering world was buzzing, trying to figure out how they pulled it off. But the latest clues suggest Tesla's ambition is even bigger. They're not just swapping one magnet type for another, they're coming full circle, back to the ideas of their original induction motor, but now armed with 15 years of game-changing progress in software, power electronics, and manufacturing. They're aiming to build a magnet-free motor that might not just compete with, but could even beat their legendary rare earth designs. This isn't just an evolution, it's a revolution that's been years in the making. So how is this even possible? How can a motor with no magnets go head-to-head with the world's best permanent magnet motors? The answer isn't a single new material, but a combination of key technologies Tesla has been perfecting for years. It's a win for smart engineering over raw material limits. In the past, induction motors and other magnet-free designs had big drawbacks. Induction motors were less efficient, especially at low speeds. For decades, everyone agreed, for a smooth, powerful, and efficient EV, you needed permanent magnets. That thinking is now officially outdated. The game has been changed by three things: power electronics, software control, and manufacturing innovation. First, power electronics. Besides the motor itself, the heart of an EV's drive unit is the inverter. This is the electronic brain that takes DC power from the battery and turns it into AC power the motor needs. But a modern inverter does so much more. It can control the frequency, phase, and shape of that AC power with mind-blowing precision. Tesla has been relentless in improving its inverters, focusing on the semiconductor switches inside. They were one of the first car makers to go all in on silicon-carbide semiconductors. SiC chips can switch on and off way faster, handle more heat, and work at higher voltages with much less energy loss than old-school silicon. This high-speed, super-efficient switching is what unlocks the true potential of magnet-free motors. For an induction or reluctance motor to run well at all sorts of speeds, it needs a very complex and constantly changing diet of electrical pulses. Old, slow inverters just couldn't keep up, which led to poor efficiency and that annoying jerkiness. But modern SiC inverters can create the exact optimized electrical field needed at any given millisecond, basically tricking a simple copper and steel rotor into acting with the power and grace of a permanent magnet motor. The second and maybe most important piece of the puzzle is software. At its heart, Tesla is as much a software company as a car company, and that philosophy goes deep into the powertrain. The motor and inverter are just the hardware. The software is the soul. It's the complex control algorithms that tell the inverter exactly what to do. This field is called field-oriented control. Basically, the software creates a complete digital twin of the motor's magnetic field in real time. Sensors are constantly feeding it data on the motor's speed, temperature, and current. The algorithm crunches these numbers and calculates the perfect electrical input to generate the right amount of torque with the highest possible efficiency, all while keeping vibrations to a minimum. Think of it like this: a permanent magnet motor is like a musician playing one powerful, simple chord that's always on. A magnet-free motor, guided by advanced software, is like a master concert pianist playing a complex symphony. The pianist's fingers, the inverter, fly across the keys, playing thousands of individual notes a second to create music, or torque, that is perfectly suited to the moment. Loud and powerful when you need it, quiet and efficient when you don't. Tesla's decade of data from millions of cars gives them a huge advantage in perfecting these algorithms. They can predict how the motor will act under any condition and optimize it on the fly. Finally, there's manufacturing. To make a magnet-free motor that is both powerful and compact, you have to push the physical parts to their absolute limits. This means using new winding methods to cram more copper into the stator for a stronger magnetic field. It means using advanced cooling to pull heat away, letting the motor run harder for longer without getting too hot. It means designing rotors with complex shapes perfected by computer simulations to squeeze out every last bit of torque. By combining these three things, fast power electronics, brilliant software, and advanced manufacturing, Tesla is on the verge of doing what was once considered impossible: a magnet-free motor that's cheap, tough, and incredibly powerful. It will depend not on exotic materials from a shaky supply chain, but on the simple, abundant resources of copper, steel, and human ingenuity. It's also a more durable design. Permanent magnets can slowly get weaker over time with heat, but a motor built from steel and copper coils will keep its original strength for years, reducing wear and long-term costs. So what does it all mean? What happens when the world's top EV maker creates a high-performance motor that costs way less than current designs and has zero geopolitical supply risk? The implications aren't just big, they're game-changing. The first and most obvious impact is cost. At that same 2023 Investor Day, Tesla said they aim to produce their next-generation drive unit for under $1,000. That number is a really big deal. It's the key that could unlock a truly affordable mass-market electric car, the long-rumored $25,000 Tesla. Right now, the drive unit is one of the most expensive parts of an EV after the battery. A powerful permanent magnet motor is filled with thousands of dollars worth of rare earth materials. By getting rid of them, Tesla can slash the motor's cost. This isn't just a number on a spreadsheet, it's the difference between an EV being a luxury item and an EV being the standard choice for everyone. It's the final piece of the puzzle in making electric cars cheaper to build and buy than gas-powered ones. Second, this move completely de-risks Tesla's supply chain. While other car makers will still be nervously watching trade talks and commodity reports from China, Tesla will have removed itself from that whole drama. Their motor will be made from copper, steel, and aluminum, materials you can get from stable sources all over the world. This gives Tesla an incredible competitive advantage in manufacturing stability and cost control. While rivals might have to suddenly hike prices or halt production because of a rare earth shortage, Tesla's factories will just keep humming along. It's a strategic checkmate that secures their manufacturing future for the next decade. Third, this new motor design is incredibly scalable. The same basic engineering and software can be used in a whole range of vehicles. A small single motor could power a cheap city car. A dual motor setup could power a new, more efficient Model 3 or Model Y. And a high-power tri-motor version could even show up in the Tesla Semi or the next-gen Roadster. This flexibility is key to Tesla's master plan to speed up the world's shift to sustainable energy. They're not just designing one motor for one car, they're creating a technology platform for their entire future lineup. This breakthrough also sends a shockwave through the rest of the car industry. For years, legacy automakers have been playing catch-up to Tesla's lead in batteries and software. Now, just as they're starting to roll out their own competitive permanent magnet motors, Tesla has changed the game again. They've basically made the current generation of EV motor tech obsolete before it's even been fully adopted. Other automakers and suppliers are now scrambling to develop their own magnet-free systems, but they are years behind Tesla's all-in-one approach of hardware, software, and manufacturing. This forces the whole industry to make a choice: keep investing in a technology that relies on a risky supply chain, or start the long, expensive process of trying to copy Tesla's new magnet-free playbook. Ultimately, this new engine is more than just a piece of hardware. It represents a shift in philosophy. It is a declaration of independence from volatile markets, from geopolitical games, and from the accepted rules of engineering. It proves that the road to a sustainable future doesn't have to be paved with compromises. It shows that with relentless innovation, the cleanest solution can also be the cheapest and most dependable. From the AC induction motor in the first Model S to the hybrid magnet motor in the Model 3, Tesla's story has been one of constant evolution, always chasing that perfect mix of performance, efficiency, and cost. Now they've come full circle, but with a level of sophistication nobody could have imagined a decade ago. They didn't just find a cheaper alternative to rare earth magnets, they've made magnets irrelevant. They are replacing a dependency on finite, dirty materials with an abundance of engineering brilliance. They are trading a weakness in materials for a strength in software and electronics, a field they have a massive and growing lead. This magnet-free motor isn't just another part, It's the key to Tesla's next chapter. It's what will lock in their manufacturing dominance for years to come. And it's what will send every other automaker on the planet back to the drawing board. No one saw this coming because they were all looking for a new material. They were looking in the ground. Tesla, as always, was looking at the first principles of physics and software, and they found a better way. This isn't just a new engine. It's a statement that the race for the future of transportation is far from over, and Tesla has just started a new lap. But now I want to hear from you. What do you think this means for the EV industry? Is this the checkmate move that solidifies Tesla's lead for the next decade? Or will competitors be able to catch up? Let us know your thoughts in the comments below. And if you found this breakdown interesting and want to stay ahead of the curve on the tech that's shaping our world, make sure to subscribe and hit that notification bell. You won't want to miss what we have coming next.